Look up at the night sky, and you see only the surface of a deeper reality. Behind the beautiful chaos of swirling galaxies and glittering stars, an invisible architecture dictates every cosmic event. These are the unseen forces that govern everything, from the frantic dance of the smallest particles to the majestic sweep of the largest structures in existence. By the end of this journey, you will understand 30 of the most profound architects of reality itself. We will explore the mysterious pressure tearing the cosmos apart and the ghostly matter holding it together. What if the stability of your own body relies on a cosmic field you cannot feel? Which of these hidden forces do you suspect is the most powerful? Our universe is not merely expanding, it is accelerating. The most powerful force in the cosmos is also the most mysterious, a repulsive pressure woven into the fabric of space itself. We call this force dark energy. Its discovery in the late 1990s sent shockwaves through the scientific community. Astronomers were observing distant stellar explosions, known as Type 1, a supernova, to measure how fast the universe was flying apart. They expected to find the expansion was slowing down, pulled back by the collective gravity of all matter. Instead, they found the opposite. The most distant galaxies were receding at a speed that defied all logic, as if an unseen hand was pushing them apart faster and faster. This was the fingerprint of dark energy, a force that overwhelms gravity itself on the largest scales. The leading explanation for this bizarre phenomenon is something Albert Einstein first proposed, then later called his greatest blunder, the cosmological constant. This idea suggests that empty space is not truly empty. It possesses a fundamental energy, a constant tension that causes space itself to stretch. Think of the universe as a loaf of raisin bread baking in an oven. The dough represents space, and the raisins are galaxies. As the dough expands, every raisin moves away from every other raisin. Now, imagine the yeast in the dough suddenly becomes more active, making the loaf rise faster and faster. That yeast is dark energy, an accelerating force inherent to the dough of spacetime. Yet this explanation opens a deeper chasm of uncertainty. We do not know what dark energy is. Is it truly a constant property of the vacuum, or is it a dynamic field that changes over time? A concept scientists call quintessence. The sheer dominance of this mystery is staggering. Dark energy is estimated to constitute about 68% of the entire energy content of the universe. This means the force driving the ultimate fate of everything we see is almost entirely unknown to us. It is the greatest unsolved problem in physics, a silent, invisible pressure that holds the keys to the final destiny of the cosmos. While dark energy pushes the cosmos apart, another unseen force holds it together. This is the cosmic glue, dark matter, an invisible substance that binds galaxies and dictates the large-scale structure of our universe. You cannot see it, touch it, or detect it with any telescope that observes light, yet its gravitational pull is undeniable. The first compelling clue emerged from the way galaxies spin. In the 1930s, astronomer Fritz Zwicky noticed something strange about a distant cluster of galaxies. The individual galaxies were moving so fast that the cluster's gravity should not have been able to hold them together. It was as if the entire system was filled with a huge amount of unseen mass, providing the extra gravitational glue. Decades later, Vera Rubin provided even stronger evidence by studying the rotation of individual galaxies. She found that stars at the outer edges of spiral galaxies orbit just as fast as those near the center. According to the laws of gravity, this should be impossible. The visible matter alone does not provide enough gravitational pull to keep these high-speed stars from flying off into intergalactic space. The only explanation is a massive, invisible halo of dark matter enveloping each galaxy, its gravity keeping the stars in check. Another line of evidence comes from a phenomenon called gravitational lensing. The immense gravity of a massive object, like a galaxy cluster, can warp the fabric of space-time around it. This warping acts like a lens, bending and distorting the light from objects behind it. By measuring how much the light is bent, astronomers can calculate the total mass of the foreground cluster. Time and again, they find that the visible matter accounts for only a tiny fraction of the total mass required to create such a powerful lens. The rest is the signature of dark matter. So what is this mysterious substance? It is not made of atoms or any particles we know. The leading candidate is a hypothetical particle known as a WIMP, which stands for Weakly Interacting Massive Particle. As the name suggests, these particles would have mass and interact with normal matter only through gravity and the weak nuclear force, making them incredibly difficult to detect. Deep underground, in mines and tunnels shielded from cosmic rays, experiments are searching for the faintest tremor of a WIMP colliding with an atomic nucleus. Another promising candidate is the action, a particle that is trillions of times lighter than an electron, but could exist in such vast numbers that it accounts for the missing mass. The hunt for these particles is one of the most challenging quests in modern science. We are surrounded by this cosmic phantom, this gravitational skeleton that shapes everything we see, yet it remains just beyond our grasp. Gravity is the force we think we know, the gentle hand that keeps our feet on the ground and our world in orbit. But its true nature is far more bizarre and magnificent than a simple pull. Albert Einstein revealed that gravity is not a force in the traditional sense, but a consequence of geometry. Picture the fabric of the universe as a vast, taut rubber sheet. Place a heavy object like a star on that sheet, and it creates a deep well. A smaller object, like a planet, rolling near this well will naturally curve into its depression, not because of a mysterious pull, but because it is following the curved path of the sheet itself. This is the essence of general relativity. Massive objects do not attract each other. They warp the very space-time around them, and what we perceive as gravity is simply objects following these cosmic curves. This curvature dictates everything from the falling of an apple to the precise orbit of Mars. Its influence scales up to an unimaginable degree, forging the largest structures in existence. Without spacetime's curvature, clouds of gas and dust would never collapse to form stars and planets. The same warping creates the most extreme objects in the cosmos. When a massive star dies, its core collapses under its own weight, warping spacetime so severely that it punches a hole in the universe, creating a black hole from which not even light can escape. Yet for all its cosmic power, gravity is paradoxically the weakest of the four fundamental forces. The tiny magnet on your refrigerator can lift a paperclip, effortlessly overcoming the gravitational pull of the entire Earth. This incredible weakness is one of physics' most profound puzzles. Why is the force that sculpts galaxies, that holds the universe together on the grandest scale, so feeble in our everyday world? The answer remains hidden, a secret that may lie in the very nature of spacetime itself, or in dimensions of reality we cannot yet perceive. Yet this gravitational weakness is utterly dwarfed by the power contained within a single atom. Deep inside the heart of every nucleus, a force of unbelievable strength wages a constant, silent war. This is the strong nuclear force, the ultimate cosmic glue. Without it, every atom in your body and in the universe itself would instantly fly apart. Its primary job is twofold. First, it binds the fundamental building blocks known as quarks together to form protons and neutrons. Second, and just as crucially, it overcomes the fierce repulsion between positively charged protons, holding the entire atomic nucleus together. The electromagnetic force wants to push the protons apart with incredible violence, but the strong force is, as its name implies, strong enough to win. It is about 100 times more powerful than electromagnetism and a staggering 10 to the 38 times. That is a 1 with 38 zeros after it, stronger than gravity. This force is carried by peculiar particles called gluons. The name is perfectly chosen, as these particles are quite literally the glue that binds the nucleus. But the rules of this binding are unlike anything in our everyday world. They are governed by a property whimsically named color charge. This has nothing to do with the colors we see. It is simply a convenient label for a type of charge that comes in three varieties, which physicists call red, green, and blue. For a nucleus to be stable, these color charges must cancel each other out, resulting in a neutral or white state. This is where the gluons come in. They constantly shuttle between quarks, changing their color charges in an endless, frenetic dance that maintains the bond. This bizarre system of rules is the foundation of quantum chromodynamics, the theory of the strong force. It is this force that makes matter possible. The energy that powers the sun and every other star in the sky is a direct result of the strong nuclear force at work. Inside a star's core, the intense pressure and heat force protons to fuse. During this process, a tiny fraction of their mass is converted into a vast amount of energy, as described by Einstein's famous equation. This conversion only happens because the strong force is binding the new, heavier nucleus together more tightly than the original ones. The energy released is the leftover binding energy, the force's signature written in starlight. Every bit of warmth you feel from the sun is a message from this most powerful of cosmic bonds, a fundamental reason why anything exists at all. But for all its incredible strength, the nuclear force is a prisoner. It creates stable, enduring structures, locking matter into a predictable form. Yet without a way to break those bonds and rearrange the pieces, the universe would be a dull, inert place. This is the vital role of the weak nuclear force, the cosmic alchemist that transforms one element into another. Its most famous effect is radioactive decay, the process where an unstable atom spontaneously changes, releasing energy. In a block of uranium, for instance, atoms are slowly, inevitably transforming into lead. This decay happens because the weak force allows a fundamental change to occur deep inside the nucleus. It can literally turn one type of quark into another. A neutron, which is made of one up quark and two down quarks, can be transformed into a proton, which is made of two up quarks and one down quark. During this process, the neutron spits out an electron and an almost undetectable particle called an antineutrino. This transformation is the key to the entire process. The weak force is mediated by incredibly massive particles known as the W and Z bosons. Their immense mass is the reason the weak force is so short-ranged and weak compared to the strong force. It is a specialized tool, not a universal glue. Without this transformative power, the universe would be a very different place. In the furious heart of the sun, the strong force slams protons together to form helium. But that process relies on a crucial first step, where the weak force turns a proton into a neutron, allowing a heavier particle to form. This is the slow, rate-limiting step that governs the sun's long, stable life. Its importance only grows in the most violent stellar explosions. When a massive star goes supernova, a blizzard of neutrons is created. These neutrons rapidly bombard atomic nuclei, building up heavier and heavier elements. But this process creates unstable, neutron-rich nuclei that would simply fall apart without the weak force. It provides a stabilizing hand, transforming excess neutrons into protons through beta decay, creating the stable, heavier elements that make up our world. The gold in a wedding ring, the iodine in your medicine, the uranium deep within the earth, all were forged in these cataclysmic events, their very existence dependent on the subtle, transformative power of the weak force. It is the quiet artist that painted the entire periodic table. While the weak force works its subtle alchemy inside the nucleus, a far more familiar power orchestrates the world outside it. Electromagnetism is the artist of the visible universe, the force behind every chemical bond, every beam of light, and every spark of thought in your brain. This is the force of attraction and repulsion carried by the massless particle we call the photon. Its influence is everywhere. The very structure of an atom, with electrons buzzing in a cloud around a central nucleus, is a delicate balance between the electromagnetic force and the rules of quantum mechanics. The negatively charged electrons are held in their orbits by their powerful attraction to the positively charged protons within the nucleus. But this is only the beginning. When atoms approach one another, it is the electromagnetic interactions between their electron clouds that decide whether they will repel or link together. This is the foundation of all chemistry. The formation of every molecule, from simple water to complex DNA, is a dance choreographed by electromagnetism. It dictates the hardness of diamond, the fluidity of water, and the specific shape of every protein in your body. This force has an infinite range and manifests in two complementary ways, as a simple electric force and as magnetism, two sides of the same coin. A stationary electric charge creates an electric field, while a moving charge creates a magnetic field. This connection is what allows an electric current to generate a magnetic field strong enough to power a motor, and conversely, a moving magnet to induce an electric current in a wire, the principle behind power generation. This duality is what builds complexity. The fact that like charges repel and opposite charges attract is what prevents the world from collapsing into a formless blob. It allows for structure and stability, for the intricate shapes of crystals and the vast architecture of molecules. Your own nervous system is a masterpiece of electromagnetic engineering. When a neuron fires, it is because charged sodium and potassium ions rush across a cell membrane, driven by electric fields. This creates a tiny voltage spike that races along the nerve fiber, a literal electrical signal that carries your thoughts, senses, and commands. Every sensation you have ever felt was transmitted by this fundamental force. Yet, for all its pervasive power, electromagnetism reveals a deeper unity at the extremes of nature. At energies higher than those found in any particle accelerator on Earth, electromagnetism and the weak nuclear force cease to be separate entities. They merge into a single, unified force called the electroweak force. In the first fleeting moments after the Big Bang, the universe was so inconceivably hot and dense that this single force reigned supreme. It was only as the cosmos expanded and cooled that this unified force split, or froze out, into the two distinct forces we observe today, much like water vapor condensing into distinct droplets of liquid and crystals of ice. This profound connection tells us that the forces we perceive as separate and unique are merely different facets of a single, underlying cosmic principle, a hidden symmetry written into the laws of reality itself. This same electromagnetic force reveals an even deeper strangeness when we probe the nature of nothingness itself. We think of empty space as a perfect void, a silent and featureless stage upon which the cosmic drama plays out. But this is an illusion. At the tiniest imaginable scales, the vacuum of space is a seething, bubbling foam, alive with frenetic activity. This is the realm of quantum fluctuations, where particles and their antiparticle counterparts spontaneously blink into existence for an impossibly brief moment before annihilating each other and vanishing. These are not mere mathematical tricks. They are a direct and unavoidable consequence of one of quantum theory's core principles, the Heisenberg uncertainty principle. This fundamental law tells us that we can never know both the exact energy of a system and the exact time for which it possesses that energy. There is always a tiny, inherent fuzziness. This uncertainty provides a loophole, a tiny loan of energy that the universe can borrow to create something from nothing, as long as it is paid back almost instantly. For a fleeting moment, shorter than any tick of a clock, particle-antiparticle pairs are born from the void. We call these virtual particles, and their ghostly existence has tangible, measurable consequences. You can actually witness the pressure of this quantum foam, Place two perfectly smooth, uncharged metal plates extremely close together in a vacuum. In the narrow gap between them, only certain wavelengths of virtual particles can flicker into being. Outside the plates, all wavelengths are possible. This creates a pressure difference, with more virtual particles pushing on the outside of the plates than on the inside. The plates are gently pushed together by the weight of nothingness itself. This real, measurable force is called the Casimir effect, a direct fingerprint of the universe's hidden turmoil. An even more profound consequence emerges at the edge of a black hole. Normally, a virtual particle pair will annihilate, paying back its energy debt to the universe. But if this pair pops into existence right at the event horizon, the point of no return, a bizarre thing can happen. One particle might fall inward, crossing the horizon and disappearing forever. Its partner, now stranded outside, has no one to annihilate with. The debt cannot be repaid. This orphaned particle becomes real, carrying away energy. From the perspective of a distant observer, the black hole appears to be glowing, slowly leaking radiation and evaporating. This is Hawking radiation, a process driven entirely by quantum fluctuations that ultimately causes black holes to shrink and die. The very fabric of reality, it seems, is built upon a foundation of restless, chaotic energy, a constant simmering that shapes the fate of everything, from the emptiness between your fingers to the most destructive objects in the cosmos. These same fleeting quantum fluctuations, the very texture of empty space, left a permanent mark on the entire cosmos. How could such microscopic chaos possibly dictate the grand architecture of the universe? The answer lies in a monumental event that occurred in the first fraction of a second after the Big Bang, a period known as cosmic inflation. During this unimaginably brief moment, the universe underwent an exponential growth spurt, expanding faster than the speed of light and inflating from a subatomic speck to a volume far larger than our entire observable universe. As space itself stretched at a phenomenal rate, it did not smooth things out. Instead, it magnified the tiny quantum jitters that were inherent to the newborn cosmos. The minute density variations in the primordial quantum foam, fluctuations that were once smaller than a single proton, were stretched across vast cosmic distances. Where a slightly denser patch of this quantum soup existed, it created a tiny gravitational well. Where it was slightly less dense, a gravitational hill formed. These minute ripples in gravity became the cosmic blueprint for everything to come. After inflation ended, the universe continued to expand, but at a much more sedate pace. Gravity began its slow, patient work on the blueprint left behind. Over hundreds of millions of years, those slightly denser regions, those primordial gravitational seeds, began to pull in more and more matter. Dark matter acted as a scaffolding, and normal matter, primarily hydrogen and helium gas, flowed into these gravitational potholes. The hills and valleys imprinted by quantum fluctuations became the sites of the first galaxies, stars, and eventually, planets. The entire cosmic web, with its vast voids and brilliant filaments of galaxies, is a direct reflection of that initial quantum noise, amplified to a macroscopic scale. We can still see the faint echo of this process today. The cosmic microwave background radiation, the afterglow of the Big Bang, is not perfectly uniform. It contains tiny temperature variations, mere millionths of a degree, that map directly onto those initial density fluctuations. These are the imprints of the quantum seeds, the fossilized ripples that gave rise to every structure in the universe. The spiral arms of the Milky Way, the countless stars in the night sky, even the planet you stand on, all owe their ultimate origin to the restless, unpredictable churn of the quantum vacuum. The largest structures in existence were born from the smallest possible vibrations, a direct link between the realm of the impossibly tiny and the magnificently vast. The cosmic blueprint was set by quantum whispers, but for the universe to build anything lasting, it needed substance. It required mass, This brings us to a field so fundamental that without it, reality would be a formless, chaotic blur. This is the Higgs field, an invisible energy field that permeates every cubic inch of the cosmos, giving elementary particles their mass. Think of the entire universe as filled with an invisible, intangible molasses. As fundamental particles move through this cosmic treacle, they interact with the Higgs field. Some particles, like photons, which are the particles of light, waltz through without any interaction at all. They remain massless, zipping through the universe at the ultimate speed limit. But other particles, like quarks and electrons, interact with this field strongly. They get bogged down, struggling to move through the cosmic syrup. This resistance to motion is what we perceive and measure as mass. Without this interaction, every particle would be like light, hurtling through space at the speed of light. There would be no atoms, no chemistry, no planets, and no people. The universe would be a soup of massless radiation, forever flying apart and never cohering into anything solid. The confirmation of this incredible idea came with the discovery of its associated particle, the Higgs boson. You can think of the Higgs field as an ocean and the Higgs boson as a splash. When enough energy is concentrated in one place, like within the giant particle colliders buried deep underground, it can excite the Higgs field, creating a ripple that manifests as the Higgs boson. Detecting this fleeting particle was the goal of one of the largest scientific experiments ever conducted. In 2012, scientists at CERN announced they had found it, a monumental triumph that confirmed the existence of the very mechanism that endows the universe with substance. The importance of this field cannot be overstated. Mass is not an inherent property of a particle. It is an acquired characteristic, a gift from the universe's pervasive energy field. This is why the Higgs field is so crucial for stability. If electrons had no mass, they would not be captured into orbit around atomic nuclei. Atoms could not form. The delicate balance of forces that allows protons and neutrons to cluster into nuclei, and electrons to swarm around them, would be completely undone. The Higgs field provides the inertia that allows matter to clump, to slow down, and to build the complex structures we see today. It is the cosmic anchor that tames the frantic energy of the Big Bang, transforming a blinding flash into a stable, material universe where things can truly exist. Yet this cosmic anchor of mass cannot fully explain another profound mystery, a connection so intimate it seems to defy space and time itself. Two particles, born from the same quantum event, can become entwined in a state of perfect correlation. Measure one, and you instantly know the state of its partner, even if that partner is on the other side of the galaxy. This is quantum entanglement, a phenomenon so strange that Albert Einstein himself derided it as spooky action at a distance. The spookiness lies in the instantaneous nature of the link. Imagine you have a pair of magic gloves. You put one glove in a box and send it on a rocket to Mars. The moment you open your box on Earth and see you have a left-handed glove, you know with absolute certainty that the glove on Mars is the right-handed one. This seems logical, but in the quantum world it is not that simple. Before you look, the glove is not a left glove or a right glove. It exists in a blurry superposition of both possibilities. It is only the act of you opening the box, the act of measurement, that forces it to choose a definite state, left or right. The truly bizarre part is that this act of measurement on Earth seems to force its entangled partner on Mars to instantly assume the opposite state. Information about the outcome appears to travel between them faster than light, a direct challenge to Einstein's theory of relativity. For decades, physicists debated whether this was a true violation of physics or if the particles were simply carrying hidden instructions, like a pre-arranged code, that determined their outcomes from the moment they were created. The question was settled by a brilliant physicist named John Bell. He devised a mathematical test, now known as Bell's theorem, which could distinguish between hidden variables and true quantum entanglement. When experiments were finally performed, the results were unequivocal. The universe chose spookiness. The particles were not following a secret script. Their connection was real and instantaneous. This has staggering implications for the nature of reality. It suggests that at a fundamental level, the universe is not composed of separate, independent objects. Instead, it is a deeply interconnected web where the properties we observe are not local, but relational. They are defined by their connections to other things. This bizarre connection is not just a philosophical curiosity. It is the foundation for emerging technologies like quantum computing. A classical computer bit is either a 0 or a 1. A quantum bit or qubit can be a 0, a 1, or both at the same time, thanks to superposition. But the real power comes from entanglement. By entangling multiple qubits, a quantum computer can explore a vast number of possibilities simultaneously, solving certain problems in minutes that would take a classical computer billions of years. This potential power forces us to confront the deepest questions of all. What does this say about the world we live in? Does a particle have a definite reality before we measure it? Or do we, as observers, play a role in bringing that reality into being? The debate over how to interpret this continues, with theories ranging from the many worlds interpretation, where every possible outcome actually happens in a branching multiverse, to the idea that our classical perception of reality is merely a superficial layer over a far stranger, interconnected quantum whole. The spooky action Einstein questioned may be the most profound clue we have to the true architecture of existence. This same restless quantum foam holds an even deeper secret, a hidden energy woven into the void. Every fleeting fluctuation, every virtual particle pair blinking in and out of existence, contributes a tiny amount of energy to the vacuum of space itself. When physicists calculate the sum total of this activity, they arrive at a staggering number. This is the vacuum energy, also known as zero-point energy, and it represents the lowest possible energy state that empty space can possess. It is the hum of the universe's engine at idle. This background energy of the cosmos is not zero. It is a positive, constant value, and it exerts a negative pressure on the fabric of space-time. This description should sound familiar. A form of energy inherent to empty space, causing a repulsive gravitational effect that pushes the cosmos apart. This is precisely why vacuum energy is the leading candidate to explain the mystery of dark energy. The quantum jitters of the vacuum could be the very yeast causing our cosmic bread to rise at an ever-increasing rate. Yet this elegant idea is plagued by one of the most embarrassing and profound problems in all of science. When theorists try to calculate the expected value of the vacuum energy using our best theories of quantum mechanics, they get a number that is catastrophically large. We are not talking about a small difference. The theoretical prediction is a 1 followed by 120 zeros times greater than the value we actually observe for dark energy. This is not just a little wrong. It is the worst theoretical prediction in the history of physics. To put this absurd discrepancy into perspective, it is the difference between the energy stored in a single drop of water and the energy contained within every ocean, lake, and river on Earth, multiplied by the mass of 1 billion galaxies. This monumental failure is known as the cosmological constant problem. How can the energy of the vacuum, which should be unimaginably powerful, be so incredibly feeble in reality? Why is the observed dark energy so much weaker than the calculation suggests? Some physicists believe there must be a perfect, but unknown, cancellation mechanism, where different contributions to the vacuum energy somehow balance out to nearly zero, leaving behind only the tiny remnant we see as dark energy. Others speculate that our understanding of the vacuum itself is fundamentally flawed, or that the universe is not described by a single vacuum, but by a vast landscape of possible vacuums, each with its own energy value. In this multiverse scenario, we simply happen to live in one of the rare bubbles where the vacuum energy is exceptionally small. a cosmic coincidence that allows for galaxies and life to form. The cosmological constant problem is a glaring signpost, pointing toward a deep flaw in our marriage of quantum theory and gravity. Solving it may require nothing less than a complete revolution in physics, a new theory that can finally tell us what truly fills the silence of empty space. To explain the universe we see, we must return to its very first moments, to a force so potent it set the entire cosmic stage. This is the driving engine of cosmic inflation, a hypothetical field that caused the universe to expand at an exponential rate, far faster than the speed of light, in a span of time almost too brief to comprehend. This theory solves two of cosmology's greatest puzzles. The first is the horizon problem. Look at the cosmic microwave background in opposite directions of the sky. These regions are so far apart that light, traveling since the beginning of time, should not have had a chance to reach from one to the other. They should be completely disconnected, like two strangers on opposite sides of the planet who have never met. Yet their temperatures are identical to an astonishing degree. How did these distant regions coordinate themselves if they were never in contact? Inflation provides the answer. Before the rapid expansion, the entire observable universe was a tiny, subatomic patch that was in intimate thermal contact. It was all causally connected. Then, inflation blew this tiny, uniform patch up to a size larger than our entire visible cosmos, preserving that initial uniformity across vast distances. The second puzzle is the flatness problem. Measurements show that the geometry of our universe is incredibly flat, meaning parallel lines will never meet or diverge. For this to be true after billions of years of evolution, the density of the early universe had to be fine-tuned to a precision of 1 part in 10 to the power of 60. It is like balancing a pencil on its tip for billions of years. Inflation naturally forces the universe toward flatness. Imagine drawing a small, wavy circle on the surface of a balloon. As you inflate the balloon to an enormous size, that tiny section of the surface you can see becomes flatter and flatter. Inflation did the same to the cosmos, stretching any initial curvature to the point of imperceptible flatness. The most compelling evidence for this incredible event is written in the ancient light of the cosmic microwave background. The tiny temperature fluctuations we detect are precisely the kind of pattern predicted by inflation, the magnified quantum seeds stretched across the sky. The search is now on for the particle associated with this inflationary field, sometimes called the inflaton. Finding this particle would be the ultimate confirmation, revealing the specific mechanism that gave our universe its form and its fate. The bizarre rules of quantum mechanics suggest that even a vacuum can buzz with energy. But what if some fields are not anchored to reality in the way we assume? This brings us to one of the most speculative concepts in theoretical physics, the tachyonic field. The name comes from the hypothetical particle associated with it, the tachyon, a particle that, by its very nature, would always travel faster than light. The idea stems from a peculiar twist in Einstein's theory of relativity. The equations tell us that nothing with real mass can ever reach or exceed the speed of light. As an object accelerates, its mass effectively increases, requiring more and more energy to go faster, making light speed an impossible barrier. But the mathematics also allows for a solution where a particle is born already moving faster than light. For such a particle to slow down to the speed of light would require an infinite amount of energy. The defining characteristic of this tachyon is not speed alone, but its so-called imaginary mass. This does not mean the mass is a figment of our imagination. Imaginary mass is a mathematical term, describing a quantity that, when squared, gives a negative number. In the simplest terms, a tachyon exists on the other side of the light-speed barrier, in a realm where the normal rules of cause and effect are turned upside down. One of the most serious theoretical roles for such a field is in a process called spontaneous symmetry breaking. This is the mechanism that gives particles their mass via the Higgs field. In fact, the mathematics of the Higgs field itself has a tachyonic quality in its initial, unstable state. Before the Higgs field settled into its current, stable value throughout the universe, it is theorized to have existed in a high-energy, symmetric state. This state was unstable, like a pencil perfectly balanced on its tip. The slightest quantum fluctuation would cause it to fall or roll down into a stable, lower-energy state, breaking the original symmetry. This roll from instability to stability is described by a tachyon-like instability. So, in a way, the very process that gave mass to the universe may have been initiated by a brief, primordial tachyonic shudder. The most mind-bending implications, however, lie in the realm of causality. If tachyons exist, they could potentially be used to send messages backwards in time. This arises from the strange geometry of faster-than-light travel in relativity. From the perspective of some observers, a tachyon signal could be received before it was ever sent, creating a paradox that violates our fundamental understanding of cause and effect. It is important to stress that despite decades of searching, not a single shred of experimental evidence for tachyons has ever been found. They remain a fascinating mathematical possibility, a ghost in the equations of string theory and other advanced models, reminding us that the fabric of reality might be woven with threads we have not even begun to pull. The search for the graviton takes us to the very edge of known physics. This is the hypothetical particle believed to carry the force of gravity, the missing messenger in our quantum understanding of the cosmos. We have already seen how the other fundamental forces are transmitted by their own carrier particles. The electromagnetic force uses the photon, the strong force uses gluons, and the weak force uses the W and Z bosons. This elegant framework works perfectly for 3 of the 4 forces. But gravity, the force that sculpts the universe on its grandest scales, stubbornly refuses to fit into this quantum box. The graviton is the proposed solution, a particle that would communicate gravitational attraction in discrete packets, or quanta, just as a photon communicates the electromagnetic force. According to the theory, every time an object attracts another through gravity, it is because a ceaseless exchange of these ghostly gravitons is occurring between them. The mathematics suggest the graviton must be a massless particle, like the photon, and must have a spin of 2, a unique property that distinguishes it from all other force carriers. Finding this particle would be the final, triumphant step in confirming that gravity is, at its heart, a quantum force just like the others. So why have we not found it? The problem is gravity's profound weakness. To detect a single graviton directly, we would need a detector so massive and so sensitive it borders on the absurd. Imagine a machine made of pure lead, weighing as much as the planet Jupiter, and placed in orbit around a neutron star. Even then, the signal from one graviton would likely be drowned out by the constant background noise of the universe. The gravitational interaction is just that incredibly feeble. The force that holds galaxies together is, in the quantum realm, a faint whisper lost in a hurricane. This is why our current particle colliders, which can create and detect other force carriers, are utterly powerless to produce a graviton. The energy required is trillions upon trillions of times greater than what our most powerful machines can achieve. Yet, the hunt is not entirely hopeless. We are probing the edges of quantum gravity through other means. The LIGO Observatory, which directly detected gravitational waves for the first time in 2015, provides an incredible indirect window. Those ripples in spacetime caused by colliding black holes are a classical phenomenon, a vast wave of gravitational energy. But if you could look closely enough at that wave, the theory suggests you would see it is composed of countless individual gravitons, all working in concert. Detecting the individual particles within that wave is far beyond our current technology. But simply observing the wave itself confirms that gravity can be transmitted in a way that is compatible with a particle theory. The discovery of the graviton would be more than just adding another particle to the list. It would be the key that unlocks the universe's deepest secret, a final theory of quantum gravity, often called the theory of everything. Such a theory would seamlessly weave together the colossal realm of general relativity with the spooky, probabilistic world of quantum mechanics. It would describe the birth of the universe and the fiery heart of a black hole with a single, unified set of equations. The graviton is the last, elusive piece of that cosmic puzzle, a ghostly particle whose discovery would forever change our understanding of reality itself. A powerful magnet always has two inseparable poles, north and south. No matter how many times you cut it in half, you will only create smaller magnets, each with its own north and south. This is a fundamental rule of our classical world, but it is a rule that theoretical physics insists should be broken. The search is for a magnetic monopole, a hypothetical particle that would be a pure, isolated north or south magnetic pole. Its existence is a direct prediction of grand unified theories, ambitious frameworks that attempt to merge the electromagnetic, weak, and strong nuclear forces into a single, elegant force. These theories suggest that in the extreme energies of the universe's first moments, such monopoles should have been forged in abundance. They would be incredibly massive, perhaps as heavy as a bacterium yet smaller than a proton, making them cosmic relics of unimaginable density. Yet, despite decades of meticulous searching, from deep within moon rocks to the pristine ice of the South Pole, not a single confirmed monopole has ever been found. This absence is a major cosmological puzzle known as the monopole problem. If grand unified theories are correct, the early universe should have been flooded with these magnetic relics. Their sheer weight and stability would have dramatically altered the evolution of the cosmos, likely preventing the formation of galaxies as we know them. The fact that our universe is not dominated by monopoles was a key motivation for the theory of cosmic inflation. That brief, explosive expansion would have diluted the monopole density to virtually zero, scattering them so far apart that finding one in our entire observable universe becomes a needle in a haystack challenge of epic proportions. Beyond their role as cosmic fossils, the existence of magnetic monopoles would elegantly explain one of nature's deepest mysteries: the quantization of electric charge. Why does every charged particle in the universe carry a charge that is an exact multiple of the electron's charge? If even a single magnetic monopole existed somewhere, its magnetic charge would force electric charges to be quantized, a beautiful and necessary symmetry. The continued failure to find these particles forces us to confront a profound question. Are our grand unified theories subtly flawed? Or is our cosmos simply so vast that its rarest treasures remain hidden, waiting for a future discovery that could rewrite the very laws of electromagnetism? The rules governing the strong nuclear force contain a hidden symmetry so perfect it seems too good to be true. This is the strong CP problem, a deep mystery in the heart of the atom. The equations of quantum chromodynamics allow for a process that should violate two fundamental symmetries simultaneously: charge and parity. In essence, this should make the neutron possess a tiny, measurable electric dipole moment, behaving like a microscopic compass needle. The most precise experiments, however, find nothing. The neutron is perfectly round, its electric charges balanced with an exquisite precision that defies our expectations. This perfect cancellation seems like a cosmic coincidence, a fine-tuning so severe it demands an explanation. The most elegant solution is a new cosmic field, the action field, proposed in the 1970s. This field acts as a universal correction mechanism, dynamically adjusting itself to cancel out any symmetry violation, forcing the neutron to remain perfectly neutral. The beauty of this solution is that the action field, while solving this profound particle physics puzzle, also produces a particle, the action. This particle would be incredibly light, potentially trillions of times lighter than an electron, and interact with ordinary matter only very, very weakly. This makes it a perfect candidate for the mysterious substance we call dark matter. Actions would not be fast and hot like neutrinos, but slow and cold, moving sluggishly through the cosmos and clumping together under gravity to form the invisible scaffolding of galaxies. Billions of these ghostly particles could be streaming through your body every second, their presence betrayed only by the faintest of whispers. The hunt for this whisper is underway in laboratories around the world. The most sensitive search is conducted by the Action Dark Matter E experiment, or ADMX. It functions like a cosmic radio receiver, tuned to listen for actions converting into photons. The heart of the experiment is a powerful magnet housed inside a resonant cavity, cooled to near absolute zero to eliminate thermal noise. If actions are indeed the dark matter, they should permeate this magnetic field. The theory predicts that, very rarely, an action will interact with the magnetic field and transform into a single, very low-energy microwave photon. ADMX is designed to detect that single, specific note amid the universe's cacophony. It is a hunt for a ghost, a particle born from a theoretical necessity that might also be the invisible glue holding the cosmos together. Finding it would be a double triumph, solving one of the deepest puzzles in particle physics while finally revealing the identity of the universe's dominant matter. Deep within the most extreme environments in the universe, a subtle quantum imbalance can generate raw power. This is the chiral magnetic effect, a phenomenon where a fundamental handedness in particles, combined with a magnetic field, creates an electric current out of nothing but asymmetry itself. To understand this, you first need to grasp the idea of chirality or handedness. Think about your own hands. Your left and right hands are mirror images, but you cannot simply rotate one to become the other. In the same way, certain fundamental particles can have a left-handed or right-handed spin, depending on the direction of their spin relative to their motion. In most circumstances, the laws of physics treat left and right equally. This is known as parity symmetry, but in some rare and exotic systems, this symmetry can be broken. Now, imagine a situation where you have a vast soup of particles, like the quark-gluon plasma, that filled the universe just micro moments after the Big Bang. In this incredibly hot, dense soup, there could be a slight excess of, say, right-handed particles over left-handed ones. This creates what physicists call a chiral imbalance. If this imbalanced soup is then subjected to an immensely powerful magnetic field, something remarkable happens. The magnetic field acts as a cosmic organizer, causing the positively charged right-handed particles to drift in one direction and the positively charged left-handed particles to drift in another. This selective drift of charges along the magnetic field lines generates a net flow of electricity, an electric current, running parallel to the magnetic field. This current emerges not from any external battery, but purely from the combination of a magnetic field and the intrinsic handedness of the particle soup. We believe this effect could be actively generating immense currents within the interiors of neutron stars. These stellar corpses possess some of the strongest magnetic fields in the cosmos, and their cores are thought to contain exotic states of matter, including quark-gluon soups. The chiral magnetic effect could be a fundamental engine powering their explosive magnetic phenomena. Beyond its raw power, this effect serves as a profound probe of nature's deepest symmetries. Its very existence helps us understand the conditions where the universe's perfect mirror symmetry breaks down. Why is the cosmos we see made of matter, with almost no antimatter? Such a vast imbalance may have its roots in processes very much like the chiral magnetic effect, where subtle asymmetries in the newborn universe were amplified into the world we know. This quantum quirk reveals that even the vacuum of space, under the right conditions, is capable of a strange and directed creativity, turning a magnetic field and a broken mirror into a river of electric charge. Einstein's curved spacetime may be missing a crucial ingredient. a subtle twist in the cosmic fabric known as torsion. While general relativity masterfully describes how mass and energy warp the geometry of the universe, creating the gravity we experience, it treats space as a purely elastic sheet that bends and stretches. Torsion introduces a new geometric quality, a microscopic spinning or twisting of space-time itself at every point. Think of it as the difference between bending a flexible rod and also twisting it along its length. The bending is curvature, the warping we know. The twisting is torsion, an added rotation woven into the grid of reality. This concept emerges naturally when physicists attempt to extend Einstein's equations to include the intrinsic angular momentum, or quantum spin, of every fundamental particle. An electron is not just a point of charge and mass, it also perpetually spins, a fundamental property as inherent as its electric charge. In standard general relativity, this spin has no direct effect on the gravitational field. But in theories with torsion, the spin of particles becomes a source for gravity, just like their mass, causing spacetime to twist and corkscrew around them. This provides a beautifully geometric explanation for a purely quantum phenomenon, potentially bridging a long-standing gap between the worlds of the very large and the very small. One of the most profound implications links torsion directly to the accelerating expansion of the universe. In certain models, the average spin density of all the particles in the cosmos could generate a constant, repulsive torsion field that acts exactly like dark energy, pushing galaxies apart. This offers an alternative to the cosmological constant, suggesting the force driving cosmic acceleration isn't a mysterious energy in the vacuum, but a geometric consequence of the universe's total spin content. The challenge, as with so many of these cosmic mysteries, is one of detection. The effects of torsion are unimaginably tiny on human scales, completely overwhelmed by the force of ordinary curvature. To feel its influence, you would need to measure gravity in an environment of phenomenal spin density, perhaps near the rapidly rotating core of a neutron star or in the violent aftermath of the Big Bang. Current laboratory experiments and astronomical observations have so far found no evidence for this cosmic twist, placing severe limits on its possible strength. Despite this, torsion remains a vital component in several advanced theories of gravity, including Einstein-Cartan theory, which elegantly incorporates it into the fabric of general relativity. It stands as a compelling reminder that our geometric understanding of the cosmos may still be incomplete, and that the true architecture of reality might be built not just on hills and valleys, but on invisible, swirling vortices of spacetime. Even Einstein's cosmological constant presents a problem of its own. It is, by definition, constant, an unchanging feature of the vacuum that pushes the universe apart at an ever-increasing rate. But what if dark energy is not a fixed property of empty space? What if it is something that evolves, a dynamic force field that has changed over the lifetime of the cosmos? This captivating possibility is known as quintessence. Imagine a fifth fundamental force, not anchored to particles like the others, but one that permeates all of space as a field that can slowly shift and roll. Unlike the static cosmological constant, the energy density of quintessence could either weaken or strengthen over billions of years. In its simplest form, you can think of it as a cosmic cousin to the Higgs field, but one whose influence is not to give particles mass, but to govern the expansion of the universe itself. The name is a deliberate echo of the ancient Greek idea of a fifth element, a pure substance beyond earth, air, fire, and water that constituted the heavenly realms. The behavior of this field would determine the ultimate fate of everything. If the field weakens over time, the acceleration of the universe could eventually slow, or even reverse into a catastrophic collapse. If it strengthens, the cosmic expansion could become even more violent, leading to a future where galaxies, stars, and even atoms are torn apart in a final event known as the Big Rip. The key to solving this mystery lies in precisely measuring the history of the universe's expansion. Astronomers are now building the most detailed three-dimensional maps of the cosmos ever conceived, charting the positions of millions of galaxies and the distances to thousands of supernovae. By observing how the rate of expansion has changed from the ancient past to the present day, they can search for the subtle fingerprint of a dynamic field. A cosmological constant would leave one specific signature in this data: a predictable and steady acceleration. Quintessence, however, would leave a different mark: a slight variation in the way acceleration has built up over cosmic time. Detecting that tiny deviation is like trying to hear a single soft note change in a symphony that has been playing for 13 billion years. The next generation of telescopes, like the Vera C. Rubin Observatory and the Nancy Grace Roman Space Telescope, are designed to be sensitive enough to listen for that note. They will measure the universe's expansion with such exquisite precision that they could finally tell us if the force shaping our cosmic destiny is a steady, eternal pressure or a living, breathing field whose story is still unfolding. The inflatoned field is the engine we have been searching for, the specific power source behind the universe's explosive birth. This hypothetical scalar field is thought to have permeated the newborn cosmos, its immense energy density overwhelming every other force. Imagine a single, all-encompassing substance whose pressure was not attractive, but powerfully repulsive. This negative pressure is the key. In our everyday world, positive pressure pushes outwards like air in a balloon. But the inflatoned field generated a gravitational repulsion, causing each region of space to push against its neighbors and driving that runaway, exponential expansion. For a fleeting fraction of a second, the inflaton's energy was the universe, dictating its frantic growth and imprinting it with quantum seeds. But such a dominant state could not last forever. Like a ball perched at the peak of a very tall hill, the inflatoned field was in a state of unstable, high-energy equilibrium. Driven by quantum jitters, it eventually began to roll down the slope of its potential energy landscape. As it rolled, it oscillated around the bottom of this cosmic valley. And these oscillations were the death of the inflationary epoch and the birth of the familiar universe. The field's tremendous pent-up energy had to go somewhere. In a process known as reheating, the energy of the oscillating inflatoned field decayed violently, transforming into a blazing, dense soup of fundamental particles, flooding the cosmos with quarks, electrons, and photons. This was the true beginning of the hot Big Bang, the moment the universe as we know it was truly born from the cold, empty expanse of inflation. The entire observable universe, all its matter and radiation, is the ashes of that decaying field, the residual heat from a fire ignited by the inflaton's final moments. The same cosmic birth that wove the fabric of space-time may have also left behind deep, structural cracks. These are cosmic strings, hypothetical one-dimensional defects that could stretch across the entire observable universe like the frayed seams of creation. They are not made of any ordinary matter. Instead, think of them as ultra-dense scars, flaws frozen into the very geometry of reality during the universe's rapid cooling in its earliest moments. As the fundamental forces we know today separated from their initial unity, the fabric of spacetime may have undergone a series of cosmic phase transitions, similar to how water freezes into ice. And just as freezing ice can trap air bubbles and form cracks, the cooling universe could have trapped immense energy into inconceivably thin, vibrating strands. A single cosmic string would be thinner than a proton, yet a single inch of it could weigh more than a mountain range. Their gravitational influence would be profound, not because they pull matter inward, but because they warp the space around them in a unique way. Space surrounding a straight cosmic string is not simply curved. It is actually missing a wedge-like slice. Picture a piece of pie. If you remove a thin slice from it, you can bend the remaining edges together to form a cone. This is the geometry around a cosmic string. If you were to travel in a perfect circle around one, you would find that your journey encompassed less than 360 degrees. This bizarre topology creates a powerful and unmistakable signature, gravitational lensing of a particularly strange kind. A galaxy directly behind a cosmic string would not appear as a single distorted smudge, but as two identical, perfect mirror images, side by side in the sky. A double vision of a single cosmic object would be the ghostly fingerprint of a string's passage. Beyond this lensing, these cosmic scars would not be static. They are theorized to vibrate, whip, and occasionally snap, sending powerful ripples through the fabric of space-time. These ripples would be a unique form of gravitational waves, a constant, faint hiss from the most violent tremors of the early universe, potentially detectable by future observatories. Finding a cosmic string would be like discovering the original blueprint for the cosmos, a fossil from the instant when the laws of physics themselves were still settling into the form we know today. The universe's fine-tuning is so precise it defies all reasonable odds. Every one of the fundamental forces we have explored exists in a perfect, narrow balance. If the strong nuclear force were just a few percent stronger, atomic nuclei would bind so tightly that hydrogen, the fuel of stars, would be scarce. If it were slightly weaker, complex elements necessary for planets and life could never form. This delicate cosmic balancing act is known as the anthropic principle, a profound observation that the universe's constants appear meticulously calibrated for our existence. The weak version of this principle is a simple statement of selection bias. We can only observe a universe capable of producing observers. In a cosmos where the constants were different, there would be no one to notice the silence. The strong version, far more controversial, suggests this fine-tuning is not an accident. It implies the universe must, in some deep sense, be compelled to allow for life and consciousness. How can we possibly explain such an improbable set of circumstances? The most compelling scientific answer lies not within our single universe, but beyond it, in the concept of a multiverse. Imagine a vast, perhaps infinite, collection of parallel universes, each with its own unique set of physical laws and constants. In most of these cosmic bubbles, the numbers are wrong. Universes where gravity crushes all structure instantly, or where electromagnetism is too weak to form atoms, remain dark and lifeless. But in a vanishingly small fraction of these universes, the dice roll just right. The constants fall into the narrow, habitable zone. We, of course, find ourselves in one of those rare, bio-friendly bubbles, not because of a grand design, but simply because we are here to ask the question. The multiverse transforms a miracle into a statistical inevitability. If you roll the dice an infinite number of times, every possible outcome, no matter how unlikely, will occur somewhere. Our existence becomes the ultimate example of observational selection, a cosmic version of a lottery winner, marveling at their luck without realizing someone had to win. This idea pushes the very boundaries of science, challenging us to consider whether our entire reality is just one page in an infinite cosmic library, a single possibility that found its voice. This subtle pressure from the void is not just a theoretical curiosity. It is a force you can measure. The Casimir effect provides a stunningly direct piece of evidence for the quantum foam's restless energy. Picture two perfectly smooth, uncharged metal plates placed incredibly close together in an absolute vacuum, separated by a gap smaller than the width of a bacterium. According to classical physics, with no electric charges or gravitational pull to speak of, nothing should happen between them. They should remain perfectly still. But they do not. An inexplicable force gently pulls them together. The secret lies in what is happening in the empty space, the vacuum between the plates. Remember those virtual particles that constantly flicker in and out of existence. They come in all possible wavelengths, like an infinite orchestra playing every note at once. However, the narrow gap between the plates acts as a physical constraint. Only certain wavelengths of virtual particles can fit between the plates, much like how only certain sound waves can resonate inside a tiny flute. Outside the plates, in the open vacuum, all wavelengths are free to appear. This creates a pressure imbalance. There are simply more virtual particles popping into being and pushing on the outside surfaces of the plates than there are pushing from the inside. The result is a net inward force, pushing the plates together. It is the weight of nothingness itself, a tangible force generated by the absence of certain possibilities in the quantum realm. This is not a large force, but it is real and measurable, a direct fingerprint of the universe's hidden turmoil. The Casimir effect transforms a philosophical idea about the nature of emptiness into a concrete physical phenomenon. It proves that the vacuum is not passive. It is a seething sea of potential, and by altering its geometry, we can harness a whisper of its power, feeling the push of the infinite against the confines of the finite. Our planet is not a stationary sphere suspended in nothingness. It is a colossal, spinning top, and as it rotates, it does something remarkable to the very space surrounding it. According to Einstein's theory, any massive rotating object will tug on the fabric of spacetime itself, causing it to twist in a subtle whirlpool motion. This phenomenon is known as frame dragging. Imagine placing a heavy, wet sphere into a bowl of thick honey and then spinning it. The honey close to the sphere would not just slide past it, it would be pulled around, forced to circulate with the spin. In the same way, the Earth's rotation drags the local frame of spacetime around with it. This effect is infinitesimally small for our planet, but it is real, and detecting it required one of the most precise experiments ever conducted. The Gravity Probe B mission was designed for this very purpose. It placed 4 of the most perfect gyroscopes ever created into a polar orbit around Earth. If spacetime were perfectly still, these gyroscopes would point in a fixed direction forever. But if frame dragging were real, the twisting spacetime around our planet would very slowly tilt the direction of their spin. The mission had to account for every possible disturbance, from solar radiation pressure to the faint magnetic fields of the spacecraft itself. After years of painstaking data collection and analysis, the results were clear. The gyroscopes had drifted. The invisible hand of the Earth's rotation had gently nudged them, confirming Einstein's prediction with stunning accuracy. While this effect is a delicate whisper around our world, it becomes a screaming vortex around a rotating black hole. This region is called the ergosphere, an oval-shaped zone of distorted spacetime surrounding the black hole's event horizon. Within the ergosphere, frame dragging is so powerful that nothing can stand still. The fabric of spacetime itself is being whipped around at such a ferocious speed that every object, even light, is forced to move in the direction of the black hole's spin. It is a cosmic maelstrom where the very concept of being stationary loses all meaning. You could fire your rocket engines at full thrust against the rotation, and you would still be swept along, a leaf caught in a hurricane of twisted geometry. This bizarre environment is not just a theoretical curiosity, it is a potential powerhouse. The Penrose process theorizes that an object could enter the ergosphere, split in two, and have one piece fall into the black hole while the other is flung out with more energy than it entered with. The black hole itself would lose a tiny amount of rotational energy, transferring it to the escaping fragment. This is the very definition of extracting energy from nothing but the twisted fabric of reality, a direct consequence of the invisible, swirling grip of frame dragging. Sometimes the most profound mysteries arrive as the faintest of whispers. Deep in the void, 2 robotic explorers, Pioneer 10 and Pioneer 11, were steadily coasting toward the edge of our solar system. Yet as scientists tracked their trajectories with exquisite precision, they noticed something deeply puzzling. Both spacecraft were experiencing a minuscule, unexpected acceleration back toward the Sun. It was an impossibly tiny push, weaker than a billionth of the gravity you feel on Earth, but it was there, and it was persistent. For years, this pioneer anomaly represented a ghost in the machine, a faint signal that perhaps our understanding of gravity was incomplete at the largest scales. Could this be the signature of dark matter tugging at the probes? Was it a flaw in Einstein's theory of general relativity itself? The scientific community was captivated. Here was a mystery born not from a cataclysm, but from the most careful, patient observation of silence. The answer, when it finally came, was a masterclass in scientific humility. After years of painstaking detective work, including the recovery of old data and the creation of complex thermal models of the spacecraft, the source was identified. It was not new physics. The anomalous acceleration was caused by the gentle, relentless push of heat. The nuclear power sources on board the Pioneers generated warmth, which radiated away from the spacecraft as infrared photons. While this radiation was mostly symmetrical, a slight imbalance existed because the spacecraft's main antenna acted as a shield, blocking heat from radiating in the forward direction. This meant just a little more heat was pushing off the back of the craft than the front. This tiny difference in thermal radiation pressure provided exactly the minuscule, sunward thrust needed to explain the anomaly. A mystery that had sparked dreams of revolutionary physics was solved by the quiet, cumulative pressure of light itself. The Pioneer anomaly stands as a powerful reminder that the universe speaks in subtle tones, and that even an explained mystery teaches us a profound lesson. The most important discoveries often begin by taking a faint, inconsistent whisper seriously, and having the patience to listen until it reveals its true voice. The same quantum fields that give particles their mass could also hide a doomsday mechanism. Our universe might be resting in a state of false stability, a precarious valley in the cosmic landscape of energy. Physicists call this a metastable vacuum. It appears solid and enduring, but it could, in theory, suddenly and catastrophically collapse into a lower, more stable energy state. This event is known as vacuum decay, and it would be the ultimate cosmic catastrophe. Picture a perfectly still pond, its surface smooth as glass. This is our current vacuum, filled with the Higgs field and all the quantum activity we have discussed. Now, imagine a single bubble spontaneously forming deep below the surface. Inside this bubble, the water has abruptly transitioned to a different state, one that is fundamentally more stable. The moment this bubble forms, its walls begin expanding outward at the speed of light. Nothing can outrun this wave of pure transformation. As the bubble expands, it does not destroy matter in the conventional sense of an explosion. It rewrites the rules of reality itself. The very laws of physics inside the bubble would be different. The strength of the nuclear forces, the existence of atoms, the nature of light, all of it would be irrevocably altered. The bubble wall is a boundary beyond which our universe, as we know it, ceases to exist. The atoms that make up your body, the forces that hold planets in orbit, the very concept of chemistry, would be instantly and permanently erased, replaced by a new, alien physics where life as we understand it is almost certainly impossible. The trigger for such an event could be almost impossibly rare. A random quantum fluctuation that provides just enough energy to push a tiny region of space over the energy barrier and into the true vacuum valley. Or it could be sparked by a high-energy event like an ultra-powerful particle collision. The terrifying beauty of vacuum decay is its finality. There would be no warning. A flash on the edge of the observable universe would be the last thing any instrument ever detected, followed by an eternal silence as the new, stable vacuum consumed all of creation. The fact that this has not happened in 13.8 billion years suggests our vacuum is incredibly long-lived, a cosmic monument to temporary stability in a sea of potential chaos. This stubborn refusal of electrons to share a space is the universe's ultimate rule against overcrowding. It is the Pauli exclusion principle, a quantum law that states two identical fermions cannot exist in the exact same quantum state. Fermions are particles like electrons, protons, and neutrons, the fundamental building blocks of matter. Think of a crowded bus where every seat is taken. You cannot sit down unless someone else gets up. In the quantum world, each electron orbiting an atom is like a seat on that bus, and the Pauli principle is the conductor ensuring no two electrons occupy the same seat with the same spin. This simple, profound rule is the bedrock of chemistry, and the reason you do not simply fall through your chair. Without it, all the electrons in an atom would collapse into the lowest, innermost orbit. There would be no variety in atomic structure, no periodic table, and no chemical bonds. The universe would be a featureless sea of identical, inert atoms. This principle of exclusion creates an effective pressure, a powerful repulsion that has nothing to do with electric charge or magnetic force. It is a purely quantum statistical resistance to being squeezed into the same identity. This resistance becomes the last line of defense in the corpse of a dead star. When a star like our Sun exhausts its nuclear fuel, it can no longer fight the inward crush of its own gravity. The core collapses until it is about the size of Earth, becoming a white dwarf. What stops it from collapsing further is not fusion, but electron degeneracy pressure. The electrons are squeezed so tightly together that they are forced into higher and higher energy states, obeying the Pauli principle. This creates an immense outward pressure that halts gravity's relentless pull. There is a limit to this support, known as the Chandrasekhar limit. If the white dwarf's mass exceeds about 1.4 times the mass of our Sun, even electron degeneracy pressure fails. Gravity wins, and the core collapses further in a cataclysmic supernova. What remains is an even denser object, a neutron star. Here, the collapse is so violent that electrons are forced to merge with protons to form neutrons. The entire star becomes a giant atomic nucleus, a city-sized sphere of pure neutrons. And once again, the Pauli exclusion principle comes to the rescue, this time in the form of neutron degeneracy pressure. The neutrons, now the dominant fermions, resist being packed into the same quantum state, creating a pressure so unimaginably strong it can support a mass greater than the Sun against total collapse into a black hole. The very solidity of the ground beneath your feet and the fierce stability of the most exotic objects in the cosmos are gifts from this single, unyielding quantum rule, a force of refusal that gives the universe its form and its endurance. Every cosmic whisper leaves a faint, enduring echo. Just as the cosmic microwave background is the ancient afterglow of the Big Bang's first light, there exists another, even more elusive relic from that primordial fire. This is the cosmic neutrino background, a vast, cold sea of ghostly particles that has been streaming through the universe since it was barely 1 second old. These are not the high-energy neutrinos produced in the hearts of stars or violent supernova today. These are the primordial neutrinos, cooled and stretched by the expansion of the cosmos to a temperature just a fraction of a degree above absolute zero. They are the oldest known fossils in existence, outnumbering the particles in the cosmic microwave background by a factor of 1 billion. Picture a universe so dense that light could not travel freely, a searing soup of radiation and matter. In that first second, neutrinos were constantly colliding with electrons and protons, trapped in the cosmic plasma. But as the universe expanded and cooled, roughly 1 second after the beginning, it suddenly became transparent to these neutrinos. They decoupled, flying free and never looking back, creating a snapshot of the infant cosmos that has been traveling for nearly 14 billion years. Detecting this specific sea of neutrinos is one of the most daunting challenges in modern science. The problem is their incredibly low energy. Today's primordial neutrinos are so sluggish that they interact with matter even less than their modern, more energetic cousins. 1 trillion of these cosmic neutrinos pass through your body every second, but they leave no trace, slipping through the vast empty spaces within your atoms as if you were not even there. To catch one would require a detector of unimaginable scale and sensitivity, a device so massive and so quiet that it could pick up the faintest whisper from the dawn of time. The information locked within these ghostly particles is priceless. They carry a direct, unaltered record of the universe in its first second of life. By studying them, we could peer back to an epoch even before the cosmic microwave background was set, testing our theories of the Big Bang and the formation of the fundamental forces. They could reveal secrets about the universe's total mass and energy density, and even provide clues about the mysterious hierarchy of neutrino masses. This faint cosmic sea is the ultimate time capsule, a silent witness to the universe's very first breath, waiting patiently for the day our technology is subtle enough to finally listen. Even the solidity of our three-dimensional world might be the grandest illusion of all. The holographic principle proposes a radical idea that the information needed to describe every event within a volume of space, every star, every planet, and every human thought, could be entirely encoded on its two-dimensional boundary. It is as if the universe we experience is a cosmic hologram, a rich and seemingly solid projection from a vast, flat surface. Think of a credit card hologram, that shiny, two-dimensional sticker that creates a stunningly detailed three-dimensional image. The sticker itself is flat, but it contains all the information necessary to project a deep, multifaceted object. In a similar way, the holographic principle suggests that the entire cosmos, with all its depth and drama, might be projected from a distant, two-dimensional shell that surrounds us. This is not saying our reality is fake, but that its fundamental workings, its most basic code, operates on a simpler, lower-dimensional surface. The mathematics behind this idea emerged from the study of black holes. Physicists discovered that the maximum amount of information a black hole can contain is not proportional to its volume, as you might expect, but to the surface area of its event horizon. This was a profound clue that perhaps the true description of a region's physics resides not within it, but on its surface. In this view, the three-dimensional space we move through is like a movie screen, and the real actors and scripts exist in the two-dimensional projector. Your perception of depth, of moving forward and backward, would be an emergent property, a consequence of complex information processing happening on the cosmic film at the edge of everything. This principle forces a complete rethinking of spacetime itself. If it is true, then locality, the idea that objects are only influenced by their immediate surroundings, might be an illusion. The true connections that bind the cosmos could be happening on that distant, two-dimensional surface, with our reality being a grand and magnificent shadow play. It suggests that the universe is fundamentally an information processor, and the laws of physics are the software running on its ultimate hardware. Could it be that every event in your life, from the smallest decision to your deepest memory, is just one line of code written on the edge of reality? But the most profound cosmic force might be the one asking the questions. We conclude our journey not with a particle or a field, but with a mystery as close as your own thoughts, the potential role of consciousness in shaping reality. This idea emerges from the heart of quantum mechanics and the puzzle of measurement. In the classic Copenhagen interpretation, a particle like an electron exists in a blurry cloud of possibilities, a superposition of all its potential states until it is observed. The act of measurement, the interaction with a measuring device, is said to collapse this wave function, forcing the particle to choose a single, definite location or property. But what exactly counts as a measurement? Is it the physical interaction with a machine, or does it require a conscious mind to register the result? This is the observer effect pushed to its most controversial limit. Some physicists and philosophers speculate that consciousness itself is not a passive byproduct of the brain, but an active participant in the cosmos. The participatory anthropic principle takes this even further, suggesting that the universe requires conscious observers to bring it into being. In this view, the cosmos and consciousness are inextricably linked. The universe came into existence with the potential for life and mind, and we, in the act of observation, complete the circuit, solidifying a reality that would otherwise remain unrealized. It is a concept that blurs the line between the physical and the mental. Could the specific, stable reality we perceive be a product of our collective observation? The scientific debate is fierce and unresolved. Many physicists argue that wave function collapse is a purely physical process, requiring no consciousness, and that introducing the mind is unnecessary and untestable. Yet, the hard problem of consciousness, the question of why and how subjective experience arises from mere matter, remains one of science's greatest challenges. This final force, whether real or illusory, forces us to confront the ultimate boundary. We have explored the invisible architecture of the cosmos, from the vacuum's quantum foam to the gravity wells of dark matter. But in the end, the most enigmatic force of all may be the one that perceives the universe, the silent witness that turns probability into experience and asks, against all odds, what it means to be here at all. We have traveled from the familiar tug of gravity to the ghostly frontiers of cosmic strings and quantum foam. These 30 unseen architects, from the concrete pillars of the Standard Model to the wildest speculations of theoretical physics, are not just abstract ideas. They are the active, breathing framework of our existence. The solid ground beneath your feet is a quantum dance of exclusion. The sunlight on your skin is a testament to nuclear alchemy, and the vast emptiness between galaxies hums with a repulsive energy we cannot yet name. Reality is not a static stage, but a dynamic, interconnected web, governed by a symphony of forces that are far stranger and more magnificent than they appear. This hidden interplay of cosmic glue, quantum whispers, and geometric twists is what allows stars to shine, planets to form, and minds to ponder the cosmos. So the next time you look up at the night sky, remember that you are not just seeing points of light. You are witnessing the grand, invisible machinery of the universe in motion. Keep looking deeper, stay curious, and let the wonder of these mysteries fuel your own explorations. We would love to hear which of these cosmic forces reshaped your understanding of reality the most. Tell us in the comments, which of these unseen architects do you find the most profoundly mind-bending?